Happy Thanksgiving. It's Paul with a little video designed to get you started on the subject of convex functionals. This will make it possible to get into the really interesting material during the week after Thanksgiving. You're familiar with the concept of a convex functional from your study of single variable calculus, in fact. If you look at a graph like this, which is usually characterized as concave up, you're aware that the second derivative is always positive. If I draw a function whose graph looks kind of like that, concave down, the second derivative is negative. What I'm going to prove is that for a convex functional like this, if the second derivative is always positive on the interval from a to b, then any place where the first derivative is equal to 0, such as that point, is not simply a local extremum, it's a global minimum. The way I'm going to do this is to pick two endpoints, a and b, and interpolate between them. 1 minus alpha times a plus alpha times b. And this x has an alpha of roughly 0.8. It's substantially closer to b than to a. Now let me apply the mean value theorem to this nice differentiable function on the interval from a to x and on the interval from x to b. When I do that, I get f of x minus f of a is equal to x minus a times f prime of a. That's the mean value theorem applied on a to x. And I get a similar result that b minus x times the derivative at some point capital B in between b and x is f of b minus f of x. In order to work with this, I've got to do a little bit of preliminary algebra. Trivially, x is equal to 1 minus alpha times x plus alpha times x. The definition of x is that it is equal to 1 minus alpha times a plus alpha times b. If I subtract the second line from the first line, I get 1 minus alpha times x minus a plus alpha times x minus b equals 0, or 1 minus alpha times x minus a equals alpha times b minus x. This is not rocket science. In this example, alpha is large, b minus x is small. That's the right-hand side. And on the left-hand side, x minus a is large, but 1 minus alpha is small. Okay, let's do a little more algebra with this. I'll take the line that I got from applying the mean value theorem on b minus x and multiply it through by alpha. And I will then take what I get by applying the mean value theorem on the interval from a to x and multiply that through by 1 minus alpha. But thanks to the little identity I just proved above, I can rewrite the right-hand side of that as alpha times b minus x times f prime of a. That's good. Now I've got f prime of b and f prime of a with a common coefficient of alpha times b minus x. And if I look carefully at this, I see when I subtract this line from the line above, I've got plus 1 minus alpha times f of a. I've got plus alpha times f of b. And I have two terms involving f of x, but after subtraction, I have just minus f of x. And that's less than alpha times b minus x times f prime of b minus f prime of a. But, now I'm on to part C. This is a difference in first derivatives. And since the second derivative exists everywhere, if I divide that by b minus a, it equals the second derivative somewhere in between capital A and capital B. And therefore, I can conclude that 1 minus alpha times f of alpha plus alpha times f of b minus f of x from there, being the second derivative somewhere on the interval between A and B is going to be greater than 0. And my conclusion is that 1 minus alpha times f of A plus alpha times f of B, which I think of as the interpolated value. You take the value at A, you take the value at B, and you take alpha times this value plus 1 minus alpha times the other value. That's greater than f evaluated at the point x, which is the interpolated point, 1 minus alpha times A plus alpha times B. And that's going to be our definition of a convex functional. A convex functional has the property that given 2 points, the interpolation of the values at those 2 points gives a bigger number than evaluating the function at the interpolated point. Now, a convex functional doesn't have to be continuous. This is our only requirement. F evaluated at the interpolated point is less than or equal to the interpolation of the values. So I can create a function by defining f of x to be x squared for positive x, but defining f of x to equal 1 if f equals 0. This function is convex on 0 to infinity. The reason is simply that the line segment joining any 2 points, one of which could be point x equals 0, is always above the graph. That's another way of characterizing a convex functional when it's a functional of just a single variable. But this works even in infinite dimensional vector spaces. On big L2, here is another functional. It's not a linear functional, but it is convex. The rule for evaluating it is square x and integrate from 0 to 1 to get a real number. What we need to check is that the interpolated value is greater than or equal to the value at the interpolated point. To get the interpolated value, I integrate x1 squared and multiply by alpha. Multiply by alpha. I integrate x2 squared, that's my second point in the domain, and multiply by 1 minus alpha. And I have to check that that's greater than the value of the functional at the interpolated point. I interpolate between x1 of t and x2 of t, square the result, multiply that out, and I did say skip the tedious algebra. You cancel out a lot of terms, and you discover that the result is equal to a quantity which is a square and therefore can't be negative, integrated from 0 to 1. It's greater than or equal to 0. Now for a really nifty result. And this is one of your last proofs, proof 3.8. Suppose we've got a convex functional defined on a convex subset of a norm space F, and this functional has on the subset C an infimum, which I will call mu. First thing I'm going to prove is that the subset where f of x equals mu is convex. This is not immediately obvious when you think about it. Imagine the function f as representing altitude in the crater of an extinct volcano, and you can think of this crater as having a flat floor. What this says is that if the altitude function is convex, then the portion of the crater where the altitude has its minimum value has to be convex. If you think about that, you could sort of imagine a set that wiggles in, wiggles out, goes around. I guess I should really try to set up a pen here. Let's see if I can do that. So you could imagine the flat bottom of the crater as looking like that. And the problem with that is that the function is not convex in that case, because if you look at that line, as well as I can draw it, up here, the value at the interpolated point is greater than the interpolation of the two values. Okay, so let's prove this. Special case. If the set omega is empty, then it's convex because the empty set is convex. This could happen if the set C is not compact. For example, it could be sort of an inverted bowl that didn't include its rim. Then the infimum would be the value as you go down to the rim, but it's not achieved anywhere. Or it could happen if f is not continuous. If I sketch a function like this, goes down, excludes that point, jumps up there. That's the infimum, but it's never achieved. Okay, so we're going to assume that omega is not the empty set. We'll consider 2 points in it, and we will consider an interpolated point, alpha x1 plus 1 minus alpha x2. Since this is a convex set, this point is also in the set. We're also assuming that f is a convex functional, and therefore the value at this interpolated point is less than or equal to the interpolated value, alpha times f of x1 plus 1 minus alpha times f of x2. But x1 and x2 are both in the set omega where the infimum is achieved, and therefore f of x1 and f of x2 are both equal to mu. So that means the right-hand side is alpha mu plus 1 minus alpha times mu, or mu, and we concluded that f of x is less than or equal to mu. However, mu is the infimum, so the only way for f of x to be less than or equal to mu is for it to be equal to mu, and we've succeeded in proving that this set is convex, that f of x is equal to mu at this interpolated point. Now for quite a nifty result. Suppose that x0 is a local minimum of f. What that means is that in some neighborhood of point x0, f of x is always greater than or equal to x0. What I'm going to prove is it's also a global minimum, that if I go out here to x1, that f of x1 is also greater than or equal to f of x0. How do we do this? Well, we have to exploit convexity, of course. So within this neighborhood, we know that f of x0 is less than or equal to f of x. Now we pick some point x1 outside the neighborhood n, but we choose a nice small alpha, so that when I take alpha times x1 plus 1 minus alpha times x0, we're on the same line but inside n. And then I can say f of x0 is, by virtue of the local minimum property, f of the point x2. But f is a convex functional, so this is less than or equal to the interpolated value, less than or equal to 1 minus alpha times the value there, plus alpha times the value there. I've got an f of x0 on the left-hand side. I've got an f of x0 on the right-hand side. I cancel out, conclude that alpha times f of x0 is less than or equal to alpha times f of x1. And since I chose alpha to be positive, it can't be 0. I'm allowed to divide by it. And I finished proving that x0 is a global minimum, that f of x0 is less than or equal to f of x1. Finally, I want to prove to you that the set above the graph of f on the convex set C is itself a convex set. In other words, that the region that is bounded below by the function graph and on the right and left by these two vertical lines is convex. How do we know this? Well, let's pick 2 points in this set. Let's pick that one and that one. When I interpolate, not a very good straight line, I apologize. When I interpolate, the interpolation of this value and that value is going to be above the graph because f is a convex functional. The interpolation of the 2 points in the domain, x1 and x2, is going to be in the set C because C is convex. Here, because C is a subinterval of the line, this is rather obvious, but the argument works when C is a convex set in a space of any number of dimensions, and therefore we know that the line segment joining 2 of these points in the set is also in the set, and the set itself is convex. Okay, to avoid difficulty with YouTube, I'm going to terminate this video now and do the last couple of pages on another one.